So, hello everyone. This is lecture 5 for error analysis. In the last lecture, we discussed some pressure measurement formulas, standard deviation, and mean, and something about the pressure and the gauges we use to measure the different ranges of pressure. And I will also share a PDF to measure the pressure and all on the Telegram channel. So, just join on that. Here, the lectures will be only targeted with the net exam. So this is lecture 5. Here today we will study the least square fitting. So most of you heard about it before. So what we do here, it's like look here. We have a number of observations at different x, the y. Now they are in a straight line. So there is nothing to calculate. Means we know the slope, we know the intercept, that is a, and the equation of line is y equal to a plus b x, where b is slope, a is intercept, and both a and b are constant. But in the physical situations, when we take the data in the physics, we don't get the this thing. We don't get a straight line. We get distributed y values on the graph, and if we know that the graph should be a straight line, then we can fit it into the straight line. Those data points, we can fit them into a straight line. So that's what we call the least square fitting here. Least square fitting here. And what is the meaning of least square fitting? Means the square terms we will take the minimize the error, means the actual value of y from the straight line, and we are measuring that point. We need to minimize that difference, square of that difference. So that's how we calculate it. Means now we have a number of data points like this, around this. Okay, so we will measure, take the all the datas, and made a straight line by all of these points. That is called the curve fit. So what we need to do, we need to find the slope and the intercept. That will give us the whole equation. And let's see first. Here our data are given x1 y1, x2 y2, x and yn. If we know the constants a and b, true value of yi, then true value of yi equal to a plus b xi. So the yi is independent, sorry, yi is dependent variable, that is on independent variable xi. So xi is independent and yi is dependent. So we will find the values of yi for different xi's by finding the a and b of the fitted curve. So these are the formulas we will use to calculate the a and b. You don't need the proof of this. I will put them in different video, but here according on the exam point of view, we don't need to find the proof. You just remember them, remember these formulas as it is. And a will be sigma xi square, that represent that first square all the terms xi, then take the summation of all the values, and same put the yi values, sum of yi values, then xi, then multiply xi yi, and then take the sum as in the denominator. We see that n sigma xi square, so x is sum of all the xi square terms, then all the sum, then square sigma x square, and in denominator we have the same thing, so we'll call it delta. Okay, so from these formulas we can find the values of a and b. And how will you find them? xy, y1, x2, y2, you have all the data points, just put it in the table. I will show you how the table will be made. Just like we have this example, means first you can fit any curve into a straight line only when you know that the output should be a straight line. Like we know that if we put a bob on a rope or a spring, we know that as we increase the mass, the length of that spring will increase. Okay, so that's how that will be a linear curve. So that's why we know that it's a linear curve, so we can just put the value of L and M. Means the independent variable is M and dependent is L. Means length will vary according to mass. So we get different readings, we take the observations, we find the different L for different mi, we take these readings in this table. So here in the place of x, that is mi, here place of y, that is li. L represent length, m represent mass. So we take these 5 readings. Okay, now we will just here we have mi li, then we will square all the mi terms, and then product mi li, then here, then we take the summation of all of these. Now we just use the formula for a and b. As I told you, the delta in denominator, that will be n sigma xi square minus sigma xi ka whole square. So just substitute the values and you will get the delta as 200. Now a will be this divided by delta. So you will get 39, and b you will get 2.06. Now you have the a and b. So you can just put in the y equal to mx plus c equation, that is for the straight line, and here it is L equal to a plus bm. Okay, here b is slope, a is intercept. So you will get a straight line like this. So in question it was asked that if the spring is stretched to 53.2 centimeters, then what will be the mass? So you can use the formula from here. You know that m equal to L minus a divided by b. So just substitute the a and b, and L is given 53 centimeters. You will get the mass. That will be 6.9 kg. So here it is the fitted curve. Okay. So this least square fit curve called the best fit curve actually. Now we have one more example. Let's see. The resistance of the sample measured as a function of temperature. Now here resistance is varying with temperature, and we know that it is also a linear curve. The temperature variation, the variation of resistance with temperature, and data are shown below. So we take these data as temperature at 2, R equal to 90, 4, 105, 6, 110, 8, 115. So we know that these should be in a straight line, but they are not in a straight line. We are getting some points in the ranges of a straight line. So we need to fit this curve. So we'll use the same formula. Here r is the dependent variable on t, so t will be x, r equal to a plus b t. Okay, now just we need to find the a and b. We use this. We made this table, and we take the all the sums. We find the delta. We find sigma x, sigma y, sigma x square, and all. Just substitute them and get the answer. We will get b equal to 4 and a equal to, well, in the question what was asked, the slope of r versus t graph using least square fit will be. So the slope was asked, so here we can see that b is slope, so we only find the b term, that came out to be 4 ohm per degree Celsius. Now see that you take this observation one time, and you repeat the observations again, then you will get the for same x values you will get something different y values, not exact these values, and for third attempt you will get something different at y values. So you will get a distribution of points around straight line, a large amount of. So there will be variation in a and b also for different observations, like you get if something for this table, then there will be different table for same observation, means y will be something different. So you will get different a for different, then third time you will get different a and b. So that's how we need to calculate the error in a also, a and b, or we need to find the error in y. Okay, uncertainty we call it. So we use these formulas. If we need to find the uncertainty in y, then we will use this formula here, yi minus, if you take the minus common, it will be a plus bxi. That is nothing but the y value we get from the curve fit. So it is nothing but yi minus y ka whole square divided by n. So it's just a standard deviation formula we use, but it is the standard formula. Now what we find the theoretically, and we it's given in the books that what actually should be used is n minus 2, not n. So if in the exam it came out, then you need to use this formula, n minus 2, not n. Okay, just remember it as it is. Now if we need to find the error in sigma a, means in the error in a, then that will be the formula will be sigma y, then this x square and delta. Okay, sigma y you will find from here, the upper side. You will substitute the value, you will get the error in a, and for the b, this formula. So delta is same as we calculated above. So that's how we can find the errors in A, B and Y. So there are two questions asked on these. So let's see the first. Both the data points and a linear fit to the current versus voltage of a resistor are shown in the graph below. If the error in the slope is this, that is 1.255 into 10 to the power minus 3 omega inverse, ohm inverse, sorry, then the value of resistance estimated from the graph is, we need to find the resistance. And as we can see in the options that with resistance we have also the errors. Okay, so we need to find the error also. Let's see. In the graph we can see that the fitted curve also given and the data points given. So we can just find the slope by the values on the y and the x, that is 1 minus 0 on the y axis and 25 minus 0 on the x axis. That will give us the slope. So 1 minus 0, 25 minus 0 equal to m. So it's the slope of the fitted curve. Okay, now we can see from this plot that it equal I upon v will be 1 upon r, right? So slope is nothing but 1 upon r. So the slope m will be equal to 1 upon r, and from here r equal to 1 upon m. R equal to 1 upon m. And we know that what is m came out to be, m was 1 by 25, so r will be 25 ohm. So we find the resistance, that is 25 ohm. Now we need to find the error in r. So to find the error in r, what we use the error propagation formula. We already studied it. If you don't know, then just see the previous lectures. So the formula is sigma r square equal to delta r by delta m square and delta m square. So here in the right hand side, it's nothing but the variables the r depends on. So here the r depends only on the m. So from here we know that sigma m is given in the question, the error in the slope, and when we differentiate r with respect to m, we will get minus 1 by m square, and then square of will give us 1 upon m4, and 1 upon m is nothing but resistance, so we'll get this term. So from here we can calculate the sigma r, that will be 0.8 ohm. So now we can write the expression for r, that is 25 plus minus 0.8 ohm. So hope you get the thing I'm trying to convey. Now there is this last question. In an experiment, the velocity of a non-relativistic neutron is determined by measuring the time. Okay, so velocity of a non-relativistic particle or neutron is determined by measuring the time it takes to travel from the source to the detector, capped at a distance L. So there is this, it's like a source here, detector here. Now it is this length between them. Okay. Assume that the error in the measurement of at a distance L, assume that the error in measurement of L is negligibly small. So this L is measured accurately. Okay. If we want to estimate the kinetic energy T of the neutron to within 5% accuracy, so just this is wrongly written here. It's just 5% error, means the error should not be greater than 5%. That is delta T by T equal is less than equal to 0.05. Okay, correct, it's not accuracy. How we define accuracy? Accuracy is 1 minus relative error. Okay, so if accuracy error is 5%, then accuracy will be 95%. It's wrongly spelled here. So we need to find the kinetic energy within 5% error, that is delta T by T less than equal to 0.05. The maximum permissible error delta T in measuring the time of flight is nearest to. So we need to find the error in T exactly, not error, the maximum permissible error in delta T. So how we will find? Just use the formula. Velocity is nothing but this distance upon time, so it is dependent on distance and time. So because in the question it is given that the velocity of a non-relativistic neutron is determined by measuring the time, so we need to take the time as a variable. So V equal to L by T, and from here kinetic energy will be this 1 by 2 mv square, 1 by 2 m L square by T square. Now we know from the rule, from the multiplication and the dividing, when we need to find the error in a formula, we use delta t by t equal to, the power will came in the front, 1 by 2 will be neglected, and m is also neglected because it's constant. So the variables are L and T. So 2 will came out delta L by L, then 2 delta T by T. Hope you get the idea. It's, I told you in the first or second lecture how we write this formulas. As delta L by L is given 0 because there is correct measurement of length, it's given in question. So we will left with delta T upon T, the small t. So we need to find, what we need to find? The maximum permissible error delta T in measuring the time. So we need to find the error in time. Error in time. So it will be delta small t by t equal to, then 2 will came into the other side. This is delta capital T by t 1 by 2, and delta t by t is given, that is 0.05, and it will give us 0.025. From here we can know the delta t, because the small t is also given, this 50 nanoseconds here. So just substitute here 50 to 0.025 will give us 1.25 nanosecond. So that will be the error in the measuring of time. So just correct here the this thing in question, it's small t, not capital T. Okay. So okay, I hope you learned something in these lectures, the error analysis. So we end it here. I will provide the PDF for the pressure measurement in the Telegram group of the channel. If you want to study more, then you can check out there. So just share these lectures and subscribe to the channel, man. Thank you.